Hello everyone, today we'll talk about the problem longest ideal subsequence. We're given a string of lowercase English characters. We want to find the longest subsequence, the length of the longest subsequence, such that when we look at adjacent characters in that subsequence, their distance in the alphabet is at most equal to k. So in other words, we have to take the original string, imagine that we cross out some of the letters, so for instance here the answer is A, C, B, D. So we get rid of this one and this one. So we cross out some of the characters in such a way that the resulting string is as long as possible. And for any two adjacent remaining characters, they are not too far apart from each other in the alphabetic order, so from A to Z. K is equal to 2, so that's the maximum distance. We're also being told that the distance in the alphabet is not cyclic, but this is just an implementation detail. So the distance between A and Z is 25, not 1, because we cannot go around the clock. We have to go backwards from Z to A or forwards from A to Z. And the same thing here. We have K equal to 3, A, B, C, D. This is okay, because this is okay even for K equal to 1, because those differences are all equal to 1. And if K is equal to 0 in particular, the answer is just repeating the same letter, and in that case it's the letter that appears the most often in our original string. The solution to this problem is quite simple, though while it is pretty simple and it's easy to come up with it independently of anything else, it is an instance of dynamic programming, a simple instance, but still, if you try to approach this problem thinking if you can solve it by dynamic programming, or perhaps if you have no other ideas and you try techniques that you know, then if you think about dynamic programming, it will fit into this problem. And then you can space optimize it into a solution that's probably easy to come up with, even not thinking about DP. One thing that may give up the fact that this is dynamic programming, or that might give you the idea to use dynamic programming, is that in general, in problems like that, dynamic programming tends to work pretty well. In particular, for problems such as longest increasing subsequence, so it would have the same initials here, a naive, well, not that naive, but an n-squared solution uses dynamic programming, and then it can also be optimized to n log n. If you're not familiar with longest increasing subsequence, I recommend that you be familiar with it, because it is quite an important and common problem to encounter. But also longest common subsequence, right? LCS, that is just solved with simple quadratic dynamic programming. So in general, when you are talking about longest subsequences that have some constraint on them, especially if that constraint only concerns ourselves at the end of that subsequence, because in this case we have two adjacent letters, so we have a long subsequence that's all okay, and we want to add another character to it, then we also have to check if this pair is okay, right? So if this distance is not greater than k, and then of course the rest we can assume that it was okay. Same thing is, for instance, about longest increasing subsequence. So if we want to add another element to an increasing subsequence, we only have to check that it increases here. And we know that this thing increases for free, right? Including this one. So when we see a situation like this, that we want to have a subsequence, a longest subsequence, that has this kind of form that we can add another element and only check it with the previous last element, then DP is probably easy to do here. And of course here, the DP is quite easy to come up with even without thinking about dynamic programming, because if we go letter by letter and maintain the length of longest ideal subsequence ending at the given letter, so ending at A, ending at B, ending at C, then we see a new letter, let's say E, then how can we create a new ideal subsequence ending at E? We can take E by itself. We can take the previous longest subsequence ending at E, so the previous one here. But also, if k is more than 0, we can go up or down a few steps. So here to D, here to F, and add 1 to those. And so we only have to maintain 26 numbers, right? Because this is the size of the alphabet. And we keep those 26 numbers. At first they are all 0. Whenever we see a letter, we try to append it to all the... So add 1 to length of every subsequence ending at a character, such that if that was the last character of a previous ideal subsequence, then we would not break the rule about k by adding our current character to it. So let's see the code. The code is, as you can see, quite short and simple. We'll be keeping for every character the length of the longest ideal string ending at that character. We're going to be going character by character. This is just calculating the number from 0 to 25 inclusive. So this is the index to our DP array. And now our result is either 1, we take just this character, or the previous value at this index, so the previous longest ideal subsequence ending at that character specifically. And then we have to go and try to take the DP of another character and add 1 to it from current index minus k to current index plus k. And since, of course, in range, this part is inclusive, this part is exclusive, then we have to add 1 here. So this is the DP at our position after reading this letter. When we go through all the letters, then the maximum of all those DPs is our answer. And in particular, if we look at which index the DP is greatest, then we know that this is the last letter of that longest ideal subsequence that we found.